Hello, and welcome to Lecture 4 of the Acceleration Unit in Phys 1104, which is going to be all about what happens when our acceleration isn't constant. I'm going to be reusing a lot of ideas that I've already introduced you to, and so I want to remind you of some of them to start. First of all, if you remember how we found the instantaneous velocity, we realized that average velocities were displacements over time intervals, and as you let the time intervals get smaller, you take the limit as delta t goes to 0, you approach the slope of the tangent line, and we call that the derivative. The other thing I want to remind you of is that anything that you can think of as a slope of a graph is a rate of change of one thing with respect to another. That applied to velocity, it applies to acceleration. And so all of the things I said before about velocity and how you can get them from slopes is going to apply to accelerations as well, except that you're taking slopes of a v versus t graph. So that means if I have data that's allowed me to make any old x component of velocity graph versus time, then of course I can find various average accelerations from changes in velocity over the corresponding time intervals. And if I want to get closer and closer to what we would call the slope at, say, time 1, I would look at smaller and smaller time intervals. So again, I'm taking the limit as delta t goes to 0, and the slope will approach the slope of the tangent line at t1. So that's this limit, and it's what we define as the derivative. And I'll say that you can get the full acceleration vector by taking the derivative of the velocity vector, the time derivative of the velocity vector. What that really means is that you're getting these derivatives of the vx and the vy versus t graphs, and those derivatives are now the components of your acceleration vector. And I would like to keep any of you from freaking out, because there's a lot of unfamiliar mathematical notation here, and I'm sure it looks kind of scary. Don't worry about those derivatives. I'm not teaching you how to take the derivatives. You'll learn those in calculus. And I don't expect you to know how to take them at this point. All I want you to realize is that if I write something like dvx divided by dt, I'm talking about the slope of the tangent line to the vx versus t graph. A really key thing to notice here now is the pattern of the connections between these different quantities. You might very easily in an experiment have measured x components of positions, and so you can construct an x versus t curve, and you're taking the slope of that to find the x components of velocity. And now that lets you build a vx versus t curve, and again you can take the slope of it to get the x components of acceleration. And that process of determining these slopes of the curves is the thing that we mean by taking these derivatives. And also, the notation that I've just used here is pointing out, as I said earlier, that vx, this derivative, is a function of t, and likewise, so is ax. Whatever you're studying, it's important to remind yourself from time to time that as humans, our knowledge has limitations on it. And there's a limitation to our knowledge staring us in the face here. Velocity as a derivative of position comes from taking a limit as delta t goes to 0. We're taking shorter and shorter time limits. But with real data, you can't let delta t go to 0. You can't take an infinite number of data points separated by infinitesimal times. So you could ask whether we can ever know the instantaneous velocity for a real object. And similarly, the acceleration comes from the velocity data the same way, and so you can ask the same question about acceleration. Well, back up. All of this is coming from data you have on position. And that data, anyway, is measurements, and so it has limited precision. So everything we measure has a limited precision. All that's going on here is that velocity and acceleration are additionally limited by the fact that we can only let delta t get so small. Now, a lot of this talk of the distinctions between average and instantaneous velocities and accelerations might sound like pretty abstract, airy-fairy theory to you, but in fact it's extremely practical. If you're an experimentalist and you have a data set, then you have a smallest delta t that you can use. It's the delta t between a data point and the next data point, and you're stuck with it. You can't make it any smaller. And it can only give you an approximation of instantaneous velocities, which are in the end what you really want to know. That's how fast the thing is going at a specific time, or what its acceleration is at a specific time. So if you can only approximate it with these average accelerations and velocities, is there a way to improve the approximation with the data set you have? Well, let's zoom in on a pair of points and have a look. So here's the zoom in. There are the two data points that you actually have. There's a theoretical curve that you might have drawn through all of your data, and there's a tangent to it at t1. And what you can actually get out of your data easily is the slope of a line connecting the 2 points, which gives you an average acceleration in this example. Well, in this picture, of course, it doesn't look quite like the tangent, and you can't get any closer with the data you have. But notice that the slope of that line connecting 1 and 2 is seemingly a lot closer to the slope of a tangent line to a point halfway between t1 and t2. So we think this should give us an estimate for, in this case, the acceleration at a time halfway between t1 and t2. Those labels 1 and 2 are arbitrary, so we might as well call that point halfway in between t1.5, I guess. So we're using an average slope to approximate an instantaneous slope at the midpoint between the 2 points used to get that average slope. Now, you can think about this and see that this is not always going to work. So, for example, here's a curve, and here are 2 points that we've got. Let's say those are our data points, and perhaps unknown to us, the curve does that in between. Well, clearly the line connecting the 2 points gives an extraordinarily poor approximation to the slope at the midpoint. So, for this to work, it requires that the spacing between your data points be sufficiently small, one of those marvelous vague phrases. And because this is a 15-minute video lecture in a first-year course, I'm just going to leave it at that. So now think about a motion diagram. So here's a motion diagram, and we would fill in velocity vectors something like this. And those velocity vectors, which are average velocity vectors, we're thinking of as coming from the positions. And so they're really representing approximations of velocities at these points halfway, well, not halfway in space, halfway in time, between the points of the motion diagram. And in the process I showed you in an earlier lecture for estimating the average accelerations, we're now using those to estimate accelerations. Well, those estimates should be about at the points halfway between when we know the velocities. So at 2, 3, 4, right? 1.5 and 2.5, halfway between them is 2. So let's just apply those ideas to data. Here's our cart up and down the incline, data we've seen before. And what we've now realized is that our column of x components of v here are kind of misaligned with the times. This v is probably a better approximation to v at a time halfway between these, and so on. So I'm going to insert a new column and call it t for vx, right? These are the t's that we would use for referring to these v's, and so this one is going to be found by taking the point halfway, or the time halfway between these two, which I can just get by averaging them, and so on. So that gives me a new time column, which I use for the v's. I could replot the v's, but all it's going to do is shift everything ever so slightly to the left on the v versus t plot. So now let me get my a's, and let me think about this. If I calculate an a using these two v's, it's going to give me the acceleration at the time halfway between these two times, which is at this time. So I'm going to put this acceleration here. I had to look ahead to see that. And so it's going to be this delta v over this, this delta t. And so there is my acceleration column, and I set it up so it would plot, and look at how much scatter there is in the acceleration. And this is just because we made that approximation of average velocities being treated as if they're instantaneous velocities, and then we made the approximation again, treating these velocities to get average accelerations again. And so we've made that approximation twice, and so our acceleration data is pretty noisy, and that often happens. Because the v versus t graph here is roughly a straight line, we believe our acceleration is constant. This sure doesn't look constant. We could take an average and get a single estimate of this supposedly constant acceleration. Or perhaps easier, we could just do what's called a linear regression and pull the slope off of this line. So now I need to keep a promise to you, because quite a long time ago I told you that the area under a Vx versus t graph always gives you delta x, no matter what the shape of the graph is. And it's sort of obvious for a constant Vx, but it's not obvious if Vx isn't constant. So here we go. We want the displacement from ti to tf of this object that's moving with a changing acceleration. You see the curve in the Vx versus t graph. Well, that's a difficult thing to calculate, but here's an easier thing. Here's a different imaginary object moving at a sequence of different constant velocities. And we know how to calculate its displacement during each of these time intervals. It's just the area of these rectangles. And because it's always going at nearly the same speed as the object we're interested in, this should be a pretty good approximation for the delta x we want. And note that it overestimates in a few places where the imaginary object is going a bit too fast, but it also underestimates in other places where it's going a bit too slow, and so these are going to tend to cancel. But if you're not satisfied that that's a good enough approximation, we can just take smaller time intervals in which it's going at constant velocities. And so now the area of all these rectangles is going to be an even better approximation. So taking smaller time intervals, I'll call them this lowercase delta t, gives us a better approximation. And we can just keep doing this. We're going to get closer and closer to the true delta x, and notice we're also getting closer and closer to the area under the curve. And so the area under the curve always gives us the true delta x. And again, we're letting something go to zero, a time interval go to zero. So we're summing up the area of these rectangles and letting the time intervals, which represent the widths of the rectangles, go to zero. And again, this has a name, big scary symbols. We call this thing the integral of Vx with respect to t. But you don't need to be afraid of it. You'll learn how to calculate it in calculus. I don't care if you can calculate it yet. What matters is that you know it means the area under this curve. So this completes our picture of the mathematical relationship between x and v and a. We know that x, if we take the slope of that curve, we get v, and the slope of that gives us a. But now the area under the a curve carries us back to v. Well, it's really delta v. And the area under that carries us back to x. Well, it's really delta x. And this is a manifestation of something you may eventually learn as the fundamental theorem of calculus. Doesn't sound very important, does it?